Okay, I get the full screen going here. It's early morning still, but the sun is coming up or trying to. And let's have at it. This video is about take out what's common. Take out what's common. I've been saying that for 45 to 50 years. Surprised I'm not saying it in my sleep. Before we continue, though, I do want to give a shout out to the person who wrote to me about the math village in Turkey. Very interesting. So yes, Jay Vollinger at nmhschool.org is my email, and I would appreciate you sending me more information. Looks like a fascinating place. All right, back to the video here. Take out what's common. We're going to take a look at a geometric situation. Like so many considerations, yesterday's video, we looked at x cubed equals x from a geometric standpoint. And as I say, I woke up this morning saying, well, that led to another consideration. So that's what I'm going to share now. So let's look at x to the fourth. And I don't know what to call it. I don't know how to draw it. I know it's one dimension above the cube, so that's my representation. And I will call this unit of measurement an is imaginary shape. So if there's some art students out there who can give me a better rendition of how to draw x to the fourth or its meaning, please chime in. But here's a typical algebra 1 problem. X to the fourth equals 3x squared. And how do we solve it? And the refrain is take out what's common. Set it to 0 and take out what's common. So let's explore that geometrically and see if we can understand why. All right, so if I've got an equal sign, then this drawing has to equal that drawing. And I can see the x squared, but I also need 2 more dimensions. So you can pause the video and figure out what those are, I bet. And yeah, it's going to be the square root of 3 and the square root of 3, or minus root 3 minus root 3. That's the number. And those are the numbers that work here. There are 2 other numbers that work. All right, and let's see if we can simplify this equation geometrically. Well, I see what's common here. That's common. That's common. All right? X squared's common. So if I take those out of this picture, I've got a new picture. And it's just 2 dimensions, getting me 3. And over here, it's 2 dimensions, which is a square, getting me, I guess, it's got to be 3. And then I hope you can see why plus and minus square root of 3 works. Now, let's actually look at it from a graphical standpoint. Let's look at the 2 graphs, and then we'll do it from an algebraic standpoint. And we'll see why the refrain, take out what's common, is so helpful. So x to the fourth, it's got a parabolic shape to it. From 0 to 1, it's actually putting out smaller quantities than x squared does. X to the fourth, when x is a half, is 1/16. When you square a half, you get a fourth. So, but soon, once we get past the number 1, we get more acceleration, more change, and probably should put some of those tables in. It wouldn't take long to make a quick connection to early calculus. But the bottom line is we see 3 points of intersection. And so what are those? Well, it looks like square root of 3 on the right, negative root 3 on the left, and it goes through the origin. So those are your 3 x values. This is a double root, and we'll see why in a second. But somebody at some point figured out that if you subtract 3x squared to the left side, then, those, if they're equal, then their subtraction has to equal 0. And what's the familiar refrain? Take out what's common. What was common? X squared times x squared minus 3 then becomes a mathematical sentence. And x squared, why is that working geometrically? Well, let's come back to this picture, which I erased. Okay. So I had this picture on this side with a box. All right. And what happens when x goes to 0? Well, as that x goes to 0, I'm losing a dimension. And if I'm losing a dimension, and I have a 4th dimensional picture, and one of the dimension goes to zero, well, the product goes to zero. And that becomes a very useful tool for solving lots of equations. We solve more equations with inverse operations than we do by writing products set to zero. And there's a term for writing products in. Wonder what that term is. I think I heard it in Algebra 1. Oh yes, factoring. That's what factoring is. If we factor out a couple of the dimensions of that picture, we don't have a picture anymore. And if we don't have a picture on the left, nothing on the left, nothing on the right, they're still equal. They're equal pictures. So that's what take out what's common is all about. So I can see that if that picture equals zero, x times x equals zero, then x squared minus 3 has to equal zero as well, because if that factor equals zero, the product is zero. And I think we can set x squared equal to 3, and we use inverse operations here if you want. Okay, you got your plus minus square root of 3. So writing products set to zero becomes a very important skill that can be learned at the Algebra 1 level. Let's do a very basic pattern here. Let's look at x squared minus 2x minus 8 equals 112. Okay, well, I'm not sure how to write this geometrically, but I can see that I've got some area statements here, and I might as well move that area statement to the other side. Minus 8, right? So I don't want to put, so it's minus that. I guess that's a better way of writing that. So if I have minus 8 on this side, I can move it to this side because they seem like they should go together. There's no variables. So we now have a new picture, and all these area statements on the left, which are now here, right? This is going to be x times x minus 2 equals that as a picture. And I don't see that clearly and easily. I mean, I can see it, 12 and 10, right? Is that right? Maybe I don't clearly see it. Well, let's see. Well, let's bring this to this side and use our newfound skill and see if we can set it to 0, get some information. And logically, I think we would start with x times x. We got a marker, gets us our first term. And what's going to multiply out to be 120 that are 2 apart? Well, I think the numbers 12 and 10 do kind of jump out at us. So we want minus, so minus and plus. And that's why we can see one answer is 12 and one answer is negative 10. Okay, so 12 and negative 10 seem to work. Now, we didn't have to do that from, well, let's look at the graphical first. All right, so let's go back to this line of work. Let's examine this line of work here. X squared minus 2x could have been written as x minus 2, x times x minus 2, and that gives me information. That gives me information that I have a parabola, that it goes through the origin, 0, 0, and also goes through at 2, 0. And I'm trying to figure out when it equals 112. That's a little more accurate picture. And I can see an x and another x. And is it believable that this one on the right could be, I think we said 12, and this one on the left, negative 10? I hope so, if I drew a decent enough picture. Now, that's not the only way that we could have solved that. If we're working with pictures, we could have completed the square, and that's on the quadratic playlist where I draw the completing the square geometrically. But from an algebraic standpoint, if we have a square, right, x, I guess I got to show it a little bit, x minus 2. I suppose that should be shorter than that, but we got to even off the sides, right? This is really an x minus 0. So what's the number between 0 and negative 2? Minus 1, right, or 1 unit. Not quite sure how I want to say that, but the mechanics are you cut it in half to even off the sides. And if you even off the sides, this side gets bigger, that side gets shorter, and we make a square. There's our square. But if we want it to equal what we started with, right? x minus one squared is x squared minus two x plus one. Well, there's the same. That plus one has to disappear, so we subtract one. And then you can see the completing the square process. The rest of it, let you look at that. And so taking out what's common, it's got a geometric component to it by the looks of it. And I'm just sharing that. And I don't know if that's going to help somebody, understand when somebody says, take out what's common, it's really about simplifying a picture. And then we can extrapolate and use it in many more contexts when we realize that if we bring the terms together on the left and set it to zero and can write it as a product, get a lot more useful information from doing that. All right, so there's that video, and I'll post it and hope that it maybe sparks some interesting considerations. All right, toodaloo, have a nice day.